Okay. So the question is, do we have something to measure how secure an OAuth implementation is? If we look at other security-related standards, we see that such tools actually exist. For example, here on the left side, you see the excellent SSL server test tool, where you simply enter a host name and it checks the SSL implementation running on that server for all kinds of weaknesses. On the right-hand side, you see a similar tool, in this case, inspecting the HTTP security headers of a website. So both tools are easy to use and they offer clear guidance. And you also have an easy to understand rating system to indicate how the site is doing. So inspired by these examples, we created a similar tool for the OAuth protocol called OAuch. And specifically, it's a tool designed to test OAuth server implementations. So it runs up to 150 test cases against the server, depending on the features that the server supports. And it basically acts like a malicious client that tries to find security weaknesses. Each test in the test suite corresponds to one security-related requirement in the OAuth specification of any requirement level. So basically, this means that every must, should, or may in the OAuth specification corresponds to a single test case. By the way, when I say OAuth specification, I don't only mean the original RFCs, but we also support many of the newer RFCs and drafts, including the best practices, of course. So I'm actually not going to talk a lot about the tool itself, but I do want to give you an idea of what it looks like. So the tool allows you to add sites and configure them as shown here. OAuch will also try to automatically guess as many settings as it can. For example, you don't need to specify which grants you wanted to test. But of course, other settings like the client ID and the different URIs must be entered by the user, of course. So once you run a test suite, there are actually two windows active at the same time. The overview window on the left side here is the one driving the testing process. So it shows the output of the tests and which features have been detected. The window on the right is the window that handles the authorization requests and the callbacks and so forth. So I mentioned before that there are currently 150 test cases in OAuch, but not all tests will be run for every implementation. For example, if the site doesn't implement, for instance, the Pixi extension, OAuch will obviously not run the Pixi tests on this site. Finally, when the test suite is complete, you get the results of the test run. So the results shown here are actually the results of a library implementation that was running locally. So it wasn't the implementation we saw in the previous screen recording. But here on this page, you can see which tests have failed. You can see the results of all tests, and you can also go through the logs that contain actually very detailed information for each test case. For example, here you see the individual HTTP requests, responses, the decoded codes and tokens, and so on. So it gives you a lot of detailed feedback. Okay, that was actually everything I wanted to say about the tool itself. I'm now going to switch to the analysis we did of the OAuth ecosystem. So what we did is we used our tool to test over 100 OAuth implementations, 94 of which are public implementations that are fully configured and deployed. And of these 94 implementations, 17 were OpenID Connect providers, and the other 77 were just plain OAuth to authorize API access. So in the rest of this talk, I will present a first look at the statistics we've obtained from this. So we are actually right in the middle of analyzing this data. So we haven't had the opportunity yet to, take a step back and look at the bigger picture. So unfortunately, I don't have a grand summary or a grand conclusion just yet. But instead, I'm simply going to give you the raw numbers of some of the things we tested. And I know slides with numbers are boring, but hopefully it will be interesting enough to get a glimpse of the current state of affairs of the OAuth ecosystem. Okay, so if we look at the API providers, a large majority is supporting the authorization code grant. So most of the sites that didn't support the authorization code grant actually only allowed machine-to-machine interaction. So they support the client credentials grant. And of all sites tested, there was only a single one that supported the implicit grant, but not the authorization code grant. So you could say that it's either the authorization code grant, the client credentials grant, or both. About half of the sites supported the implicit flow, which I guess isn't surprising, because it used to be a popular flow, and many sites still needed to provide backwards compatibility. As mentioned on the slide, 3% of sites actually also offered access via the password flow. So this is, in fact, an underestimate, because we did find additional sites that offered password flow access. But it was more difficult to get a client ID for these sites, for example, because you had to be a paying customer. So these sites weren't included in the analysis, but so the 3% is probably an underestimate. If we look at the OIDC servers, we see that all of them support the authorization code grant, and that the implicit and hybrid flows are both supported in 24% of the cases. So I guess from these numbers that we can conclude that the authorization code is indeed the most popular flow overall, which is great news, of course, because that's the recommendation. Now that we know which flows are implemented, let's take a look at how well they are implemented. So if we look at the API providers, we get a test case failure rate of 38%. And that's a lot, that's huge. This means that 38% of all relevant musts, shoulds, and mays from the specification are not implemented in the average site. So if we split this 38% into the different requirement levels, we get the following results. Unsurprisingly, a lot of the optional countermeasures are not implemented, but still almost 1/3 of the mandatory to implement countermeasures are also not implemented. If we look at the OIDC providers, they do a little bit better. With an average failure rate of 28% and a failure rate of 22% for the mandatory countermeasures. So that's not good news. Now, let's make it a little bit more interesting, and let's take a look at some of the statistics for specific countermeasures. So the percentages in the rest of this presentation are always for the API providers and the OIDC providers together, unless specifically mentioned otherwise. Let's start with discussing client authentication. So the large majority of sites actually support confidential clients. So this is great news. Most of them issue a client secret, and one site actually allowed the user to upload a crypto key. But of the tested sites, only one site used public clients. So these numbers actually look pretty good, except that 12% of the sites never really requested the password they've issued. So on these sites, you can exchange authorization codes, you can refresh tokens, and so forth, all without ever having to present the password. So the password is basically useless in this case. If we look at how the client ID and client secrets are transmitted to the server, the OAuth specification recommends that it is sent via the authorization header, which is definitely the safest choice. But even though servers must support this header, only 69% of them actually do. So the other servers that don't support the authorization header require that the client secret is sent via a forum post parameter, which is of course a little bit less secure. So switching to Pixi, for example, well, we would expect to see widespread support for it because the extension has been standardized for 5 years now. And the best practices have actually made it mandatory for authorization servers to support it. Unfortunately, only 12% of the API providers currently support Pixi. Most of them simply ignore the additional parameters, but some of them even specifically disallow them. So you can do authorization requests with Pixi, but you can do them without Pixi. Note that in these numbers, we don't include the OIDC servers because OIDC has a nonce parameter that can be used as an alternative to Pixi. So of the API providers that supported Pixi, none of them actually required it. So a third of them supported plain Pixi, which is not the recommended mode, but they typically also support the more secure S256 mode. And almost half of them supported code verifiers that were very short. Actually, the standard mandates a minimum length of 43 characters, I think, but these servers happily allowed code verifiers of only a few characters. A few months ago, a Pixi sidestep attack was also suggested on the OAuth IETF mailing list. We also tested whether servers were actually vulnerable to this attack, and it turns out that about half of the tested implementations were indeed vulnerable to the Pixi sidestep attack. So I added the link to the mail archive below. Okay. A big source of many of the security problems in OAuth implementations relates to the handling of redirect URIs. So the good news is that most sites actually require callback URIs to be whitelisted, but about half of them do not precisely match a received callback URI parameter with the whitelisted value. So this is, of course, against the standards. Also, when a callback URI is presented in the authorization request, it must be included also in the token request. But again, less than half of the sites actually enforce this. Okay, so as you all know, when using the authorization code grant, the authorization server generates an authorization code, which can then be exchanged for an access token. Now, of course, an important requirement is that the authorization codes can only be used once. If it is used a second time, it can be assumed that the authorization code was leaked and request must somehow must not be allowed. In addition to this, since we don't know whether the first exchange was performed by the attacker or a legitimate client, tokens granted during the first exchange should also be revoked. The majority of sites indeed do not allow multiple exchanges, with 12% also revoking previously granted access tokens, but still 12% of sites allowed a single authorization code to be exchanged multiple times. Access tokens are mostly opaque, so we found only 15% of websites that were using JSON Web Tokens as access tokens. They were typically also long enough, so the majority of access tokens is actually above the required 128 bits of entropy, and the others are typically close to that, so that's okay. But one thing that is actively discouraged by the OAuth specification is using access tokens as URI query parameters. Unfortunately, almost half of the API endpoints did accept access tokens in the URI, And in fact, this is actually an underestimate because OAuch only tries to pass the access token via the official access_token parameter. But we've also seen sites where the token could be passed via a parameter with another name, and these sites are not counted. So it's actually more than 44%. Refresh tokens can be used in 66% of the sites. Because they are an attractive target for attackers, they must of course be well protected. And the OAuth specification actually has specific requirements for them. For example, refresh tokens can be reused only if they are sender constrained. However, this requires a cryptographic key. And as I mentioned before, only one implementation that we tested supported this. So the other implementations must use refresh token rotation, where the authorization server issues a new refresh token for each refresh response. In addition, the previous refresh token must be invalidated, of course, but it must also be remembered to detect multiple exchanges. And then if later an old refresh token is presented the second time, the authorization server must assume some kind of a breach and must invalidate the active refresh token. So unfortunately, about 1 in 3 sites actually implemented this correctly and did not accept an old refresh token. The majority allowed refresh tokens to be reused multiple times, so that's not good news. But even for the sites that did not accept the old refresh token, they also never revoked the active refresh token. So they also didn't implement the guidelines fully, so to say. Of course, the point of having refresh token is that the lifetime of access tokens can be reduced. And the best practices actually say that access tokens should have a short lifetime, but they don't give a specific recommendation. In any case, OAuch tests the lifetime of these access tokens when refresh tokens are also granted. And these are the results. So about 1/3 of the access tokens are valid for less than an hour. Almost 3/4 of access tokens are valid for less than a day, but 27% of them are still valid for more than 1 day. In fact, we saw one access token that was valid for 20 years, and they even issued a refresh token with that. So I don't know if that was necessary, but yeah, you see crazy stuff. Okay, so I could go on for a while, but I don't want to bore you to death, of course, and I also wanted to leave some time for a discussion afterwards. So here are some other interesting results, but the list goes on and on, so we have many more results like this. I'll give you a moment to quickly go over them. The higher numbers are typically worse. Well, actually, they are always worse. And at the end of the line, I also added whether the countermeasure was mandatory or optional. So as you can see, the optional countermeasures perform worse than the mandatory countermeasures, but still, it's a bit dramatic to see mandatory security measures that are not implemented in about 1/3 or half of the implementations out there. And this is actually despite the fact that they were already in the original OAuth specification. Okay, so I'm going to leave it with that. So keep in mind that results I've presented here are still a work in progress, and we're still interpreting them right now. So in particular, one open question for us is, how can we quantify the security risk when an implementation doesn't implement a specific countermeasure? So currently we use the requirement levels as stated in the specifications, but I can imagine some shoulds have a higher security impact than some musts, for example. So if anyone has an opinion about this, I'd be very interested to hear it. I'm only looking with half an eye to the chat, but I saw some questions about where can I find the tool and when will it be available. So if you want to try the tool yourself, you're currently out of luck. It will be available on the site oauch.io, but it'll probably be available starting in September. So keep an eye out for that. Yes, the conclusion. So I think there are two major takeaways here. So first, it's great to have a formally verified protocol. Excellent. But we also need something to test implementations. So obviously, judging from the problems we found, it's not easy to fully implement the OAuth best practices. Second, a lot of sites are missing many of the countermeasures that are considered to be best practice. And many, if not most, of the countermeasures can actually be implemented while retaining backwards compatibility. They also do not appear that hard to implement. It can be as simple as adding the right HTTP header, for example. So there's really no reason not to do it. But of course, we need a tool to tell site owners what they have missed. Okay, with that, I'd like to thank you for listening, and I'd be happy to answer questions you might have.
Thank you, Pieter. Very interesting results, especially when we're working on new standards. It's always good to see how things are used in practice.
Mm-hmm.
I think one question that came up is, what is the overlap between this and the OpenID Connect conformance suite?
That's a good question, and one we've been asked before. So perhaps I should first start by telling how this tool came about. So actually, it's evolved from some work we were doing on OAuth. At the time, I wasn't interested in OpenID Connect, so I actually didn't look at the specification of OpenID Connect and the resources there at the beginning. And I only became aware of the test suite that OpenID Connect has after I already implemented OAuch. So there is probably some overlap. That's definitely true. Of course, I assume, so I haven't looked at the test cases of OpenID Connect in detail, but I assume, yeah, they only work for OpenID Connect, of course. And I also assume that they test the musts, so the requirements in the specifications. I'm not sure if they also test the optional countermeasures. I could be wrong. I mean, I haven't looked at it, but that's definitely something that we do in our tool with OAuch. Yeah.
Will this work be open sourced?
Yes. But again, so it'll be probably yeah, September. Yeah, starting September somewhere.
Excellent.